this is Dr. DORCAS NGIGI. We started with our experiment, and now we did the first one where we determined the focal length of our converging lens by observing an object that is very far for the lens, which we call an object at infinity. The image of that object should form at the principal focus. Now in this lesson, we are going to determine the focal length of our lens, but by a different method. We're going to determine using what we call no parallax. The no parallax method. And let's see how the method is. Now, if we have our lens, that's our lens, then I draw the principal axis to pass through the optical center. Then let's have that F and 2F. Then you have F and you have 2F. Okay? Let's say you put an object at the principal focus. If you put an object at the principal focus, any ray that comes from the object so let's say the rays are coming from the principal focus. They are coming parallel to the principal axis. I want to put our lens somewhere. This is our lens. And then behind this lens, I'm going to put a plane mirror. So that now I have my lens. And I have my plane mirror there. Like that. This is my plane mirror. Slightly behind the converging lens. Okay? Now rays are coming, let's say we have an object at F. Okay? An object is at F. Rays are coming from F. So we said any ray that is coming from F should be refracted parallel to the principal axis. Any ray that is coming from F, okay, as long as the object is at the principal focus, any ray that is coming from F should be refracted by the lens parallel to the principal axis. Okay? Now, in that case, this ray, if you put a plane mirror there, behind the lens, there's a plane mirror, then these rays, considering that they are parallel to the principal axis, then they will be hitting the mirror, the plane mirror, through the normal. What is a normal? A normal is a line that cuts another at right angle, so that the ray coming from the converging lens and the plane mirror, that's the plane mirror, they are perpendicular. They are making an angle of 90 degrees. What does that mean? It means if the ray is passing through the normal, then it will be refracted through the normal. Remember, now we are talking about refraction. A plane mirror is not a lens. It does not allow light to pass through it. So what happens once a ray of light hits an obstacle, that is a point where it cannot go through, then it is sent back, obeying the laws of refraction. What does the first law of refraction say? The angle of incidence equals to the angle of refraction. But all angles, as we know, are measured from the normal. So any angle is measured from the normal. So if the ray is passing through the normal, then the angle between the ray and the normal is 0. So the angle of incidence is 0, and so the angle of refraction is also going to be 0. Meaning the ray was incident to the plane mirror and is going to be refracted incident to the plane mirror through the normal. This is still the normal of the plane mirror at that point. That's the normal. At that point of the plane mirror, that's the normal. At At this point, that's the normal. And any ray that is passing through the normal is refracted through the normal because the angle of incidence is 0. So the angle of refraction will also be 0, okay? So these rays, after hitting the plane mirror, are going to be sent back through the same path, okay? So this is reflection. This is now reflected. So these are reflected rays. That one. These are reflected rays. Reflected because we are dealing with a plane mirror. But once they get to the lens, what did we say? Any ray that hits the lens parallel to the principal axis, remember these rays are parallel to the principal axis, is refracted through the principal focus, or at least converge somewhere. So as you can see, they are going to be converged there. So where we have our image, the image is going to be the same point. So that's the image. Now this will be the image. It's going to be true, but inverted. This is the object, okay? So these rays are coming. They are like rays. I want you to look at the principle of reversibility of light. These rays are like rays that are coming from somewhere on the focal plane, okay? The rays are coming from somewhere on the focal plane. So when they are coming from remember the principal focus is here. So any point above or below the principal focus, that is the focal plane. So when rays are coming from the focal plane, yes, it's true, they're coming from the principal focus, but after they hit the lens, they must be parallel to each other. So they are parallel to each other, like you have seen there. So they could be parallel on that direction. They could be hitting and then they move like that, but parallel to each other like that. So the plane mirror is somewhere there. Or they could converge depending on the direction of the, like now these ones, the plane mirror could be there, or they could be like this, depending on where the point is. If it is, we are deferring to this point, then they will all be straight lines like I've drawn them, okay? So don't get confused. So in this case now, we are just going to take the plane mirror. This is my converging lens. Then I'm going to take a plane mirror, and I'm going to put it behind, like that, okay? Behind it. Then what are we going to observe? The image and the object are going to form at the same point for the reasons that I've just explained. Any rays that are coming from the principal focus or focal plane, somewhere on the focal plane, after refraction by the lens, they come out parallel to each other. Now, if we put the plane mirror there so that these rays are perpendicular to the plane mirror, then they are sent back along the same path. So they will be sent back along the same path, like that. And after hitting the lens, then they will be converged back to the same point. So that's the experiment we are carrying out. So I come here to do the experiment with me. So here we go. So that is my plane mirror, and that is my converging lens. So I have the two, I put them together. So after putting them together, you can see this is my meter rule. This is my meter rule here. Hope you can observe it. This is the meter rule. The one I'm holding with my fingers is my meter rule. Then I have the converging lens, and the plane mirror is a plane mirror. So I put it there, okay? So I also am going to, sorry for that. Okay, I'm also going to put this white paper here to avoid reflection of my image. I don't want myself to be seen. I only want you to observe the experiment. Now, this is going to be my object. So my pen here is my object. You can see it. So I put it next to the meter rule, and I move it down until you see, I hope you can see the image inside the converging lens. You can see the image of the pen, okay? So right now they are very far. So you move the pen down until the image and the pen are tip to tip. You see that? Okay? Not yet. Okay, it's there. So you can see there should be no parallax. They should be tip to tip. So let's do it again. Right now you can see they are very different. Move the object down until use your eyes here, visual score, until you see the two are tip to tip. Then that's now that is the distance. That is what we call no parallax method. So when we do that, so now that is the image. So you move it down and up, looking through your converging lens until the two are tip to tip. Now I'm going to repeat the experiment using a ball pen. So I have a white ball pen here, you can see it. Okay, so I'm going to repeat the same. So you look through the converging lens. So I'm going to move the ball pen until it is tip to tip with its image. You see that? Okay. Now they are tip to tip. Then you measure the distance from the screen to where you have your object. Now the two are, let me go back. You can see them. You can see they are tip to tip. Leave there until they are tip to tip, you don't measure. So this is the no parallax method. So you can keep repeating it until you get very sharp image. Okay. Now they are tip to tip. Your eyes can see that they are tip to tip. Now that distance from the lens to where you have your object, now that becomes your image distance. So that is called no parallax method. We use that method also to determine the focal length. And when I measured the distance from the lens to where I have my moving object, that distance was still 5 centimeters. So that is called the no parallax method, and it's very important in determining the focal length of our converging lens. Thank you for being with me up to the end. Don't forget to share, to subscribe, to like, but most importantly, share this information with the people you know will require it and will need it very much. Until next lesson, thank you very much. Goodbye.